out if you want to do it that way, or you can ask questions directly, either approach. He's not here in that regard. I know he's very happy to move on in that, but thank you very much.
Thank you.
One thing I wanted to mention about this entire event is this is part of the 25th anniversary events for the Public Policy Center and also part of our Forkenbrock series. And I mentioned that part of the mission of the Public Policy Center is to do background research to inform policymakers, but then it's also to share that information with the public, and this is one of those forums in which we do it. And we've got an excellent group of experts, both from a policy perspective and an academic perspective today, that we're very fortunate to be able to share with you. And our first speaker is also an example of how, since the president of the Board of Regents is here, how we can play together among the Regents institutions well when we want to. And our first speaker is Chris Anderson. He's the assistant director of the Iowa State University Climate Science Program at Iowa State. We have full bios on all of the people in your folder, so I'm not going to go ahead and read through those, but what Chris is going to do is be able to bring to us sort of that overview of what kind of extreme patterns have we been seeing and where to set the stage for the rest of the day. So Chris.
Well, good morning, everybody. And by good morning, I don't mean it's a glorious day outside, isn't it? We joke about severe weather here in Iowa, and to me, 15 below wind chill is severe weather. And by good morning, I also don't mean, isn't it inspiring to sit around and talk about all the damages that our state has incurred over the last 5 years? By good morning, what I really mean is, I am really glad, sincerely glad, to see such a cross-section of leaders and agency folks who are managing our resources and in charge of our resources in the state here to demonstrate that they are concerned about changing extreme weather and that they see the need for adaptation to move forward. It's a message that climate scientists at Iowa State have been trying to get out for at least the last 5 years. And it's very hard, actually, to overcome the static that comes from the national media. The national media highlight certain aspects of climate variability and climate change. And in fact, in Iowa, some of the variability and change is very different from what you see in the headlines. And so for 5 years, we've been preaching this message of, well, we need to be sincerely focused on adapting in Iowa. And to see all of these people here today is really a very nice thing for me to see, and it really is a good morning to, it really makes this a good morning to me. So what I want to talk about is, as I was introduced, what are some of the things that we need to really focus on going forward? And in this table, I've compiled a few of the statistics just to put us on the same page on what kind of damages we have incurred recently in the state. The statistics compare the years 2000 to 2004, that's a 5-year period at the beginning of the millennium, to our most recent 5-year period, 2008 to 2012. And I've listed a few of the damaging weather events that we have in Iowa: tornado, hail, wind, flood, and also agricultural production. These are statistics that are derived from publicly available data sets. They're data collected by federal agencies. And so in some sense, they're not nearly as refined as the information you will receive later today. But it demonstrates that even in the most unrefined and coarse data sets that we have available to us, you can see clear changes that have happened in the state. In the right-hand side, what you'll see are estimates of losses that are collected by the federal agencies. These do not include things like disaster assistance or the cost of recovery. It's just a simple estimate by the federal agency of a direct loss from a damaging event. And in the two left columns are the changes in frequencies of some of these events where they're available to us. And so the money line here is actually the money. The change, as you can see, from 2000 to 2004 and then into 2008 and 12 is very dramatic for these damaging events. For tornadoes, there's a 10-fold increase in the damages and the losses that we've had in the state. For flood, there's a doubling from 1.4 billion to 2.9 billion in losses. For corn indemnities and soybean indemnities, there are also much increases in what has happened. So for corn, we've seen indemnities increase from 270 million to 2.2 billion. And for soybean, not quite the increase, but still a doubling from about 390 million to 600 million. And so what this table points out are three things that I want to carry forward in the rest of this presentation. First is that the damages are real. It's not something that we are just screaming about because we want to scream and get attention. The damages are real. In the most unrefined data sets that we have available to us, these very coarse statistics collected by the federal agencies, you can see that we have much higher damages in these particular sectors. Also, the damages are across many sectors in the state. It's not just flood, it's not just agriculture, it's also property insurance, it's also many other things in the state. So the second point is then what the rest of my talk talks about, which is which of these damages do climate scientists think are more likely to continue to be something we need to deal with going forward. And I'll give you some answers now and explain the rationale through the rest of the slides. And the answers are the damages that come from tornado, hail, and wind are more than likely due to just bad luck. They're not something, there has not been a change that leads us to expect that these damages are going to continue to go forward. And the same can be said about actually our damages owing to drought. The droughts of 2012 and 2013 both occurred within patterns that historically we would expect drought to occur. And it's just bad luck that they happen on back-to-back years. The one change that is very, very obvious to climate scientists is the change in the rainfall that we get in the state. And so anything that is affected by the rainfall is something that we have to reconsider going forward. The third point is, while that may sound like I'm diminishing the need to plan for broad damages across all the sectors in the state, that's not the case. And the reason is if the frequency of one damaging event changes, then that means the frequency of compound damaging events can change. For example, we've had a drought, flood year, and then a drought. We had drought in the summer of 2012, flood in the spring of 2013, and drought again in the summer of 2013. And so if we didn't have a change in the frequency of heavy rainfall in the spring, maybe what we would be talking about is a drought and a drought. Two really bad years back to back, just really bad luck. Instead, what we're talking about is an exponential increase in the amount, a multiplicative increase in the amount of damage that was done because we had that bad luck intermixed with the new reality of more rainfall in the springtime. So my next slide begins to demonstrate some good news in Iowa. Before I go from this slide, though, I do want to point out that, of course, I haven't included all of the losses and all of the damages we've experienced in the state on this table. There are also losses and damages to our natural resources that are not quantified here in this table. There are losses and damages to human health that are not included in this table. And for the succinctness of this table and for this presentation, those have not been included here, but they should not be overlooked either. So the good news is the tornado damage that we've received is actually very, very low. And the frequency of tornadoes we've had recently is very, very low compared to our past. This plot shows the time history in the state of Iowa of damaging tornado reports. And the words EF2 to EF5 are damage ratings that are applied to tornadoes. And these types of tornadoes are the most damaging that we have. And it's also the data record that is the most reliable. And we can take it back to the early 1950s, and what you see is there was a period in the 1960s when the number of these damaging tornadoes was much, much higher. Currently, we've been around 5 damaging tornadoes per year in the state. And back in that 5-year period, we were more like 25 damaging tornadoes per year in the state. And so this gets back to my third point in the last slide, which is nothing has changed about our climate, and we could actually have a 5-year period like the 1960s again. We could see that happen again. Tornadoes, though happening by chance and not necessarily changing in their frequency, if we have bad luck, and that's combined with the increased rainfall that we have and the damages we receive from that, it could be a very, very bad situation. And I just want to give one more slide showing about how the tornadoes have changed. It's not necessarily that tornadoes have gone away from the state of Iowa or from the nation as a whole. It's just that they've been redistributed. And in the right-hand side, you will see the tornado tracks from 2008 through 2012. And on the left-hand side, it's in the 5-year period in the 1960s when they were frequent in Iowa. And these data are taken directly from the Storm Prediction Center's website, and they have this nice graphical interface that takes these GIS files and creates these maps for you. If you're interested in looking year by year or for a particular tornado event that you remember from some time in your life, you can go to their webpage and draw these maps. What you see is the cluster of tornadoes in the last 5 years has been focused in the southeast. And you may remember all of the damage that they've experienced down around Birmingham and Springfield, Missouri, and even Memphis, Tennessee, and Nashville, Tennessee. So they have been the unlucky ones most recently. Well, that's the end of the good news. Sorry to say. I'm going to switch now into my second point of that first slide, which is why do we think that rainfall change is here to stay? And first I want to look back at the historical records to give us a little bit of a baseline to have a common base to discuss more about. And just very simply, if we look back to the 1890s, in fact 1870s, when our climate records were established in the state of Iowa, we can count the number of years that have been very, very wet years. So the annual precipitation that occurs only 10% of the time in a 140-year record, that means 14 of the years, is highlighted in red in this slide. And if these years are distributed evenly, or approximately evenly throughout the 140-year record, then we would say that what has happened recently has just been bad luck. It's been random. But as you can see, the red bars are really focused and are much more frequent in the last 20 to 30 years. And that's one of the clearest signals of a climate change in the entire United States that exists right now. The change in the rainfall in the Midwest is a very, very clear signal. It's something that climate scientists have recognized since the late 1990s, and they have reported on this in climate assessments for the nation for at least a decade. For us, wet year sets the stage for problems, but what really causes the problems is when it's a rainy day. And we can take those exact same records and count the number of rainy days. When the number of rainy days exceeds, again, the 10th percentile, that is the rainiest of the rainy days, then we can indicate at each station when this happens and count the number of stations. And the red bars here show when the state has had a large number of stations experience these heavy rainy days. And it's the same message. The message is that recently these rainy days have happened much more frequently than any time in the last 140 years. And this is a function of our climate. It turns out that a lot of our rain comes from, as you have probably all experienced, from heavy rainy days. It's not like this everywhere. It's not like this in Seattle, for example, where they have a lot of drizzle days. But in Iowa, that's just the way it is. So when we see evidence that the annual rainfall has changed significantly, it's not surprising that we also see heavy rainy days have also changed. And I want to show one slide that looks way forward into the future before coming back to the present. The slide that looks way forward into the future comes from climate model projections. And I don't want to get into the science of this very much, but I do want to show that we generate the same sort of graph with the climate projection data that we have generated with the historical observations data. And what this shows is that the climate projections going forward in the 21st century show a very big increase in the number of days when, in the number of, years. This is just in the wet springs, excuse me. So this shows a very big increase in the number of wet springs that occur going forward to the latter half of this century. And so these three pieces of information are coming together for us to make strong statements that our rainfall statistics have changed. First, it's clear that it's happened in the past. Second, we know that rainfall changes, how rainfall changes in the Midwest, that it changes in the annual rainfall by changes in the heavy rain days. And third, our climate models going forward, when simulating a warmer climate, point to a continued increase in the frequency of wet springs, which is our wettest time of the year. So I want to give you a little bit of a science background on why the water has changed in the Midwest, and then I want to close up with what I think is a very important aspect of today's meeting that needs to persist going forward. So this plot really doesn't do justice to the ideas behind it. It's a scientific plot, and that gray blob in the middle has a lot of information in it, even though you can't really discern anything from it other than it's a gray blob. And what happens is this blob quantifies where all the rainfall in the upper Midwest originates from. And so what it says is that the rainfall in the upper Mississippi River Basin originates from the land surface of the states to our south and southwest, all the way down into Texas and along the Gulf Coast. And it also originates directly off of the ocean, from the Gulf of Mexico back to the northern tropical Atlantic and the Caribbean Sea. What happens is the water evaporates either coming out of plants or off the land or off the ocean, and it gets into the wind currents and gets transported up here and gets pulled into storms and falls as rain. But what this slide doesn't show are two important things that have happened. The first important thing is, really, this is a much more dynamic situation than what this slide shows. The water that comes from our neighboring states to our south actually itself also originates from the Gulf of Mexico and the North Tropical Atlantic. And so what you see is kind of a hopscotch pattern, if you were to be able to animate this. And so the water would originate and evaporate off of the ocean surface, get caught up in storms over Texas, Kansas, Missouri, fall onto their land surface, sit in their soil, come into plants in that area, or come right off of the soil and lakes in that area, and then get back up into the jet stream, come to Iowa, and fall as rain here. And so you'd have this really, really nice hopscotch pattern that we can't really show in this gray blob in this magazine. Instead, we use a lot of words to try and explain that. The second thing that's really important, besides the fact that all the water essentially originates from the Gulf of Mexico, Caribbean Sea, and North Tropical Atlantic, is that the temperature in those ocean waters have increased recently. And this is a really easy concept to grab because it's equivalent to a boiling pot of water on your oven. If you put a pot of water on your oven and you turn up the heat, you know steam's going to come up from it. Even if you don't get it to boiling, your cabinets or your hood above your oven will get some condensation on it. And that's what's happening in the oceans. The oceans have warmed. And because the oceans have warmed, they have more water that they release to the air. When more water gets released to the air, it gets caught up in the low-level jet stream, and it comes through this hopscotch pattern and falls in Iowa as an increase in rainfall. So to summarize how this all works, why are we having more heavy rain events? Well, there's more water in the air over the Midwest. Part of this is because we have warmer ocean conditions, and water is being transported from the warmer ocean to the north into Iowa. The other is we have an inherent moisture recycling process in this state due to our soils, our rich organic soils that we use for crops and the agricultural productivity in the state also causes our water cycle to be very efficient. When that soil gets very wet, that allows crops to pull that water into the air and makes the air more humid. That allows storms to have more water available to them. This is very different than, say, the southwestern United States, where you have very sandy soil and the water goes down into an aquifer, or even just in Nebraska, where the water can drain very rapidly compared to Iowa into an aquifer. The other point is I tried to emphasize that there are changes that have occurred. Some of these changes are because of natural cycles. That relates to the fact that we don't believe tornado frequency has changed over the long time, and it's not expected to change going forward. It's just been a natural cycle, and we were unlucky in the past, and we've been lucky recently. But part of the change is because of the greenhouse gas increases, and in particular, the warmer oceans is from the greenhouse gas increase. They are absorbing more energy into the ocean because more energy is coming from our atmosphere in the form of radiation. The current cycle that we're in, we expect to last another 10 to 20 years. It's something that climate scientists argue about a little bit. When exactly did it kick in? It looks like it kicked in the mid-90s, and these typically last 20 to 30 years. So from here on out, another 10 years, we expect this pattern to continue. So here's the evidence for why, this is the evidence for why rainfall is our main problem in the state. And the damages associated with rainfall are the damages we probably should prioritize and think about how we protect ourselves going forward. That also means we need to consider the whole picture of damaging weather events and say, well, if this one type of weather event, damaging rainfall, has changed, now what is the likelihood that we could have compound very bad events together? But what I want to finish on is what I think is really important aspects, which is to develop dialogue. And that's part of the good morning that we have here, which is there are so many different types of people represented that it's a good place to begin this dialogue. And I hope that this can also be an event that helps us to sustain this dialogue. I know that in 2010 there was a report that was released that really prodded the state to create report and review mechanisms so there was an ongoing assessment and dialogue process. And I think the University of Iowa now has done a good job of pulling a whole bunch of people together across the many sectors in the state, and building off of the 2010 report and building off of this event, we can continue to establish a sustained dialogue. Now I want to give 3 examples of why it's important. First, I'm a citizen of Ames, I'm a citizen of Iowa, and I'm involved in the politics there as well. And after the 2010 flood, I was able to work with the city and the university to think about what kind of statistics should they be considering in their flood mitigation plans and studies. And one thing I presented, along with Gene Tockley, who's not here today, who is the director of the climate science program at Iowa State, we suggested that, well, this is a community forum. Ultimately, the statistics that we want to see reflected in our mitigation policies have to be the statistics collectively we want to have. And we suggested there are 3 ways that we could present, 3 types of statistics we could present to people in the state or in the city. The plot that's shown here shows I believe it's the annual average, the annual rainfall, and its relationship to the peak stream flow in the city of Ames, as measured just south of the city of Ames on the Squonk River. What it shows is that at times we have had stream flow that exceeds 300% of its normal value, and when that occurs is when rainfall exceeds 150% of its normal value. And so there's about a 2-to-1 relationship between the annual amount of rainfall we receive and the peak stream flow we experience in that state. Now that is based upon historical data, and the question is, which of those historical data do we use to estimate the frequency of hitting that marker of 150% annual rainfall? And so we suggested, well, you could use what is the current standard, the data going back to 1953 when the stream gauge was put into place. And if you use that, then you would exceed that 150% rainfall frequency 1 in 27 years. Or you could use a standard that prioritizes just the most recent period, 1980 to the present, when it's clear in our records that the rainfall statistics have changed. If you do that, then you get a frequency of 1 in 21. Or you could use a projection forward of this trend that occurred in 1980 to 2012. And if you use that case, then you get a frequency of occurrence of 1 in 9 years. And so we presented this to focus groups and to people within this community, and we let them decide which of these they wanted to plan their mitigation around. It turns out that the engineering firm scoped out ways to create flood inundation maps based upon each of the 3 processes. Another thing that came out of the 2010 report was a strong recommendation that the Department of Interior consider interim designs for for highways and bridges before that can be put into place before the Federal Highway Administration brings in new standards that reflect the expected changes in rainfall statistics. And one of the good things is that recently the Federal Highways has funded a program for us to look at 4,100 bridges across the state and their vulnerability under changing climate statistics to stream flow problems. One of the nice things that this study is allowing us to do is to be more sophisticated in thinking about how we can use climate data. And this graph shows how we are using, with the University of Iowa and the hydraulics expertise, climate projection data as a vulnerability test for a couple of pilot bridge locations in the state. In this case, that plot on the very far left is the spring rainfall from climate model projections that I showed earlier. We're using those climate model projections to go into the hydraulics models that were used and evaluated for many, many years, and also gave us much insight into the Cedar Rapids flooding event, in order to, at a select few bridges, see what the vulnerability will be under the future rainfall conditions. And then in the lower left are the stream flow traces that come out of their hydraulics. And so this is the first of its event, a first of its kind activity. It's not something that's being done anywhere else in the nation, and it's actually one of the pilot activities that the Federal Highway is funding, along with other activities, for example, coastal inundation from sea level rise. And then finally, the final reason why it's really important for us to have a sustained dialogue is that climate science itself is changing very rapidly. You heard in the last 10 years a lot of publication, a lot of PR about climate change and about the IPCC, the Intergovernmental Panel on Climate Change, and its reports. But what's coming on now is a new capability to do forecasts that are 10-year forecasts, not climate change forecasts, which are focused on the latter half of this century, but actually forecasts focused on the next 10 years. And this is an extremely new, there's only been one experiment on this. And a picture that I'm showing here is one of the first results from this first experiment. And so it's kind of a nervous, I don't know if I should be showing this picture because I don't want you to take away that this is going to be the best forecast we're going to offer. But over the next 10 years, 5 to 10 years, this system that is being developed will be rigorously tested and will become more available. And what I like to call it is a capacity to do an adaptation on forecast. And the reason why I call it that is in the emergency management field, we already have tornado warnings. We already have tornado watches. And those tornado warnings mean that a tornado is already present or it's going to occur in a few minutes. And what that community is really pushing forward is using weather models so that they can warn on forecast. Before a tornado is here, they want to be able to say, excuse me, Storm X is going to produce a tornado in 15 minutes. Go to the basement, get out of the way. And they call that warn on forecast. Well, here in climate science, we're coming close to being able to evaluate and have the capacity to do adapt on forecast. What this very first plot shows is that for the years 2016 to 2020, the expected temperature in the United States especially is expected to be lower, is forecasted to be lower than previously expected with climate change experiments. Excuse me. So I think that's a very important point to take away, because this lower temperature is coupled with the change in the hydrology cycle that we've talked about earlier. And even though they haven't shown the results from the precipitation forecasts in the Midwest, looking at this one plot, I would expect that this is evidenced in a forecast that continues to support the notion that change in heavy rainfall events should be expected for the next 5 to 10 years. Okay, so the story is this. Damaging weather in Iowa. We have had an increase in frequency of wet years and wet days, and that is likely due to very clear changes in the climate, very well-founded changes in the climate, and it's going to continue for the next decade. This has a problem not only in and of itself, but also in that it causes the sequencing and the likelihood of compound damaging events to increase. I want to say that there is some good news, which is even though our heavy rainfall has changed, we don't expect there to be an increase or a change, a significant change in tornado frequency, hail, or wind. So from that perspective, we have some good news. But in the end, what I really want to say coming out of here is as we deal with a new reality of more water in our state and how we are going to manage it, we really need to have a sustained dialogue. We don't need to have this group really interested, another group really interested. We all need to be really interested, and we all need to have a regular way of communicating with one another what advances we're making in the way that we are managing water and what advances we are making in climate scientists that you might be able to take advantage of as you make your management plans. And that's the end of my talk, and I'm not sure if I'm early or late, but My idea, first of all, was I know that the others have had panels associated with their talks, and I'm happy to be my own panel as well.
So, we do have time for one or two questions. There are cards on the table if you want to use those, or you can just ask. Yes, sir.
I'd like to ask a question about the connection you made between the heating of the Gulf, like the higher temperatures in the ocean, and the frequency or the amount of rainfall. Now, you said it was a 10 to 20-year prediction. So if we assume global warming is going to continue, that heating is going to continue, why would it be limited to 10 to 20 years? And what's the prediction? If it continues to warm, will that be more rain per hour?
Right, those are good questions, and that's part of the complexity of the climate science. I tried to impress a little bit earlier that some of our changes are by natural variations, and you've heard this a lot in the large media, national media, when they've had these debates about has climate change occurred. And for the next 10 to 20 years, the change in the Pacific Ocean temperatures, not the Gulf, but the Pacific Ocean temperatures, puts us in a state where the likelihood of drought is less. We have a lower risk of drought under this particular configuration of Pacific Ocean temperatures. This is something that was derived from temperature records that date back to the mid-1800s. And even though it has some fairly large error bars on it, because that only represents about 2 or 3 cycles of that process, we are fairly confident that it's not going to be a 5-year process or a 3-year process. It's going to be more like a 30-year process. And we're about 15 to 20 years into it. So from the perspective of the natural cycle that controls our risk for drought, we're in a low risk for drought. And the reason why I only talk about the next 10 years is because it's sometime in the 2020s with those fairly large error bars that we would expect that ocean temperature pattern to change in the Pacific and perhaps put us at higher risk for drought. That's a very tenuous thing I can say about that, but I'm just saying from the published literature, that's when we would expect the next significant change to occur. And you're right, with the increase in the Gulf of Mexico, which is our source of water, as it continues to increase, the climate projections are showing that the number of rainy years will increase. Those are most obvious in the climate projections beyond 2050, but they are certainly occurring now as well. Yeah, the question is, what is the state of expertise in modeling development in regards to whether we can apply it at the watershed level? And so that's a national discussion that has been going on in the West and a little bit in the eastern part of the United States, but a lot in the West, because they have a lot of their water managed by the Army Corps and the Bureau of Reclamation. They have their water supply in huge reservoirs. And they've asked the same exact question. And it's not just those large federal agencies, it's also large cities like Seattle and San Francisco. They need to know if the modeling, the climate science modeling we have, can allow them to pinpoint a basin in the high elevation of the mountains of the Sierras as a place where the water supply is going to change drastically. And the answer is that there is a lot of variability. So from a climate science perspective, saying that in a particular basin, what the climate change signal is going to be is a very tenuous thing. It's not something we believe we can do. On the other hand, from a perspective of the real world and managing what the real world is likely to experience in the future, the climate models are showing the ability to show the full range of rainfall that can happen in a water basin. And that allows managers to say, well, we're going to manage to this range of rainfall. And so while a climate scientist may not be able to come in and say, in this basin, the climate change signal is X%, What the models allow us to do is to say, we are going to manage to this range based upon these physically sound models that we have developed. Did I confuse the answer? Because there are two perspectives on that, and it's really hard, in my mind, to balance the climate science perspective with the management perspective. The management perspective doesn't really care what the signal is. They just want to know what the range of outcomes is so they can manage it. And the climate scientists have been very, very slow to endorse using their models in this way because they are accustomed to using models where they can understand signals, and they use models to find signals. And if they can't find a signal, then the model's kind of worthless to them. And so this is a real point of contention that has garnered a lot of, at least 15 years of discussion in the Western United States. And now we're finally discussing it here, and that Iowa DOT project I talked about is part of sorting through that question for us.